So there are some instances where for every deterministic algorithm, you can find an instance where the algorithm inspects all the leaves. Why? That's basically what he said. It's simply because as you can just set the value for the leaves that will force the algorithm to evaluate the next ones. How do you say that? That means that you will always choose the value that makes the ancestor uncertain. So basically, the whole spirit is simply to do the following. So I won't do the complete proof because it's not needed here. But basically, if you look at a subtree, the invariant that you will maintain is the following. If some of the leaves have not yet been inspected, basically what you will maintain, the invariant, simply that if in a given subtree some leaves have not yet been inspected, then the value of a tree is uncertain. Okay, it's not yet determined. So how do you do that? Simply by if you're setting the last leaf of one subtree and the other leaf is already evaluated. If you look at the subtree where there is one leaf here, which is not yet evaluated. Okay, if you look at the biggest subtree where this leaf is the last one to be evaluated. Okay, so in that case, what you know is because of this invariant, this value is not yet set. This value isn't set. You still have the choice between 0 and 1 here. Okay, because you've chosen the biggest subtree where this leaf is the only one which isn't set. Okay, and you know also by the invariant that this isn't set, but the value here can be 0 or 1. So imagine that the parent of these two is an end node. What value do you want to plug here so that it's still the invariant is conserved? Yes? 0. You want to plug a 1. Yes, you want to plug a 1 because setting this value here will give you a 0 or a 1. Okay, so you set a 1 here, and if it's an OR, then you choose this value of this leaf so that the value is 0. Okay, and then you see that you have the total freedom for these two for the choice. Okay, so you can just look. Let's run the algorithm, the deterministic algorithm, and when you inspect a node, you just set the value so that the value of the subtree is can always be 0 or 1. Okay, and you can do it recursively. So you can force any deterministic algorithm to inspect all the leaves. Okay, is it more or less clear for you? So basically, there is no escape. Okay, deterministically. The best we can do in the worst case is inspecting all the leaves. Okay? The best we can do in the worst case is inspecting all the leaves. So can you come up with a good randomized with a randomized strategy? Can you imagine some randomized strategy for this problem? This will take a lot of time. So we want to evaluate these three. So what would you suggest?
With a random access machine or with?
Yes. It's whatever.
Let's take a random path.
Yep.
If I see one for all nodes, then I don't have to explore anymore.
Yeah, but where can we win sometime? Where can we win sometime? We can win if, for instance, if the value of the OR is a 1, then at least one of the three is a 1. Okay? And as soon as I see this one, then I don't have to evaluate the other three, the other subtree. Okay? And for the end, if the end evaluates to 0, then at least one of them is 0. And if I start with this one, then I won't have to evaluate the other subtree. Okay? So what kind of randomized strategy can I just imagine? Yeah?
Each time that we see an OR, for example, we try to guess which one
And what guess means?
Randomly we...
Yeah, just choose by chance. Okay? So we will just use a very simple algorithm that does the following. So we have, yep.
We are going to show that there is an expected time in log n, I suppose? Or
Oh, no, it will not be log n, no.
Well,
In French, if you feel more comfortable.
c'est-à-dire que j'ai l'impression qu'on va montrer qu'on a, oui,
Ah non, on va montrer plus que ça.
une complexité attendue qui, en fait, est la complexité moyenne de l'algorithme déterministe.
Yes. Yep, exactly. That's what we will do. That's what we will do, but for every instances. That's more or less what we will do. But what we will show also is that it's the optimum one. We know, but we will see how to prove that it's the optimum one. Okay? So you're right. We'll more or less that's one of the way to design randomized algorithm. Okay, and it's to somehow randomly permute the structure, and then get to the random case. But it's not exactly that. I mean, what we will show exactly is that basically the spirit of the algorithm will be the average performance of the deterministic algorithm with the same leaves, where you're allowed to permute randomly left and right subtrees recursively. Okay, so it's not exactly the average performance of a deterministic algorithm. Okay, so well, it's not on a random. It's not on a random sequence of 0 and 1s. It's a different thing. Maybe it's equivalent, but I don't know. It's finer than that. The result will be finer than that. Okay, so what is the solve algorithm? So the random solve algorithm of a tree T is the following. One, choose, let R be a random bit. Okay. 2, if R equals 0, then R solve left of T. If the value of T is known, is still unknown, then R solve right of T. Okay. Else it's exactly the opposite. R solve left of T, or maybe we can rewrite it differently. Well, too late. If the value of T is still unknown, then R solved the left of t. I was rewriting the same thing, so it's right here and left there, and then okay, and then return the value of t. Okay, so you choose randomly which one of the two subtrees you will evaluate first, either the left or the right. If once you've got the value, you can say you can tell what's the value of the tree. Then you don't evaluate this one, and you output directly the value of the tree. If you still cannot evaluate the value of the tree, then you evaluate the other subtree. Okay? See, it's clear what the algorithm does? So for instance, we will try with this tree. With this tree here, so let's remove the value. So I will just run the algorithm. So I choose a random value here. I don't know. Will go left. Okay. Then I will start with the right. Then I will start with the right again, and then with the left. So the value is 0. It's an end node. The value is 0. It's an end node, so I already know that the value is 0, and I won't need to evaluate this leaf. Okay? It's an OR node. The value is 0, so I need to evaluate the other one. So I pick a random one, for instance, this one. The value is 0, so I need to evaluate the other one. And I need to evaluate 1, and then it's 1. It's an OR.
No, it's still 0. It's still 0. It's an
It's an end. Okay, sorry. So it was 0. So I don't need to evaluate this one. Thank you. And it's OR of these two, so the value is 0. But it's an end here, so I have already the value. It's 0, and I won't need to evaluate the other leaves. Okay? So now it's an OR. The value is 0. So now I have to evaluate this one, so I will pick up a random path, for instance, this one, then, for instance, this one, then this one. The value is 0. So I evaluate this one, and the value is 0. So now I don't need to evaluate the end, but I need to evaluate the other one. So I pick up this one. The value is 1. So I need to evaluate the other one. So it's 1. Then I know it's 1. Then I know it's 1. It's an OR, so I need to evaluate the other one. I will start with this one, then this one, for instance. It's an end, so I need to evaluate the other three. Okay? So now it's a 0, so it's a 1, so it's an end, so I need to evaluate the other one. So the value is 1, but it's an OR, so it's a 1. And then 1 and 1, it's 1, and then 1. Okay? So you see, I already evaluated these leaves. So a very little number of leaves. And I still got the value of the tree. So it seems to be a very good strategy to do it randomly. Okay? So we need to evaluate how many leaves will we study on average. We will inspect on expectation. Okay? So that's what we will prove. So the question is, why do we hope to visit less nodes? The reason is the following, is that, so you have an OR node here. When do you need to evaluate the two subtrees of an OR?
When the first one is 0.
So when the first one is 0, but you have probability 1/2 to get this one. So when are you sure that you will need to evaluate these two? When there are 2 zeros. Okay? If there are 2 zeros, then it's really bad. Okay? Randomness doesn't help. You will need to evaluate the two subtrees. But in that case, what's the value of the OR? 0. And for the end, what's the best case? What is the worst case for the end? When the two subtrees are 1. Okay? And in that case, the end is 1. So why are we sure that we will win something?
If you get the 1 here, then with the OR above, we will win sometimes.
Yes, exactly. The bad case for OR are the good case for AND, and reciprocally. Okay, so you may not win on one level, but on both levels you will win definitely. Okay, that's the whole spirit of it. Okay, that's exactly what we will prove. Okay? So let's say T of k is the expected number of leaves inspected in the worst case, in the worst case, yes, by are solved on a tree of 2k levels. Okay? So T of k is the expected number of leaves, the expected number of leaves inspected in the worst case by R solve. Okay, so remember that when we do a randomized algorithm, the cost of an algorithm is the max over all instances of the expected cost of A on instance I. Okay? That's how we evaluate the cost of an algorithm. Okay? When the size of instance is n. Okay? Okay, so that's exactly what we want. We want the max in the worst case, so the max over all instances of the expected number of leaves inspected by the algorithm. So, how do we evaluate that? Well, we simply do it by recurrence. Okay? So if we have 0 level, then if we have 0 level, we have just one leaf. Okay? And the value is 1. Okay? And now we try to evaluate tk plus 1, t of k plus 1. T of k plus 1, 2k levels. And 2, this means that n equals 2 to the 2k. Okay, good point. You have 2 to the 2k leaves. So tk plus 1. What is it? So we have to evaluate that. Okay. So in order to evaluate it, we'll just think about. Oops. So t to the 2k plus 1 is an OR, 2 ends, and 4 trees of size 2k levels. Okay, that's what a tree with k plus 1 level is. Okay. So we need to study 2 cases. Either the value of the OR will be 1 or 0. Okay, so let's say, if the value of the tree with k plus 1 level is 0. Okay, so again we do worst case. We do worst case analysis. Okay, so imagine that the value of the tree is 0. This means that, this implies that the value of the 2 ends and the left end and the value of the right end is 0. Okay, if the value of the OR is 0, then the value of the 2 subtrees are 0. Okay, what does this mean? This means that, imagine that for the left end, at least one of the 2, so let's say that this one, it's tk1,